History remembers the headlines. We find the bylines. This is the unsung. The origin story of the computer age is populated with familiar names. Turing, von Neumann, Jobs, Gates, figures associated with theory, hardware, or commercialization. We think of blinking lights, massive mainframes, and garage-born geniuses. But the story of how we actually talk to computers, how we moved from arcane machine code to the high-level languages that built the modern world, has a different protagonist. History remembers the creation of the computer as a feat of engineering and logic. But behind it all was a U.S. Navy officer and mathematician who was actually the architect of software abstraction. Her name was Grace Hopper, and her pivotal contribution was the radical idea that computers should adapt to human language, not the other way around. So how was the admiral who gave us the compiler, and thus the very concept of portable software, written out of the popular narrative? Grace Murray Hopper was, by any measure, an exceptional mind. She earned her PhD in mathematics from Yale in 1934, a rare achievement for anyone, let alone a woman at the time. When World War II broke out, her patriotism and intellect compelled her to serve. Despite being initially told she was too old at 34, she persisted and joined the U.S. Navy Reserve. Her assignment was to the Bureau of Ordnance Computation Project at Harvard University. There she came face to face with a 70-ton behemoth, the IBM Automatic Sequence Controlled Calculator, better known as the Mark I. Imagine this environment. It wasn't a world of sleek keyboards and graphical interfaces. This was the raw, physical frontier of computation. The Mark I was an electromechanical monster, 51 feet long and 8 feet high, filled with clicking relays, spinning shafts, and miles of wire. Programming it meant physically manipulating switches, plugging in patch cords, and feeding it instructions on long spools of paper punch tape. A single error in the tape meant finding the hole, patching it, and punching a new one. It was a painstaking, tedious process, and the prevailing wisdom was that this was simply the nature of the beast. Computers, they believed, were just incredibly fast calculators. Their job was to do arithmetic, and the human's job was to speak their complex numeric language. But Grace Hopper saw something different. Her background in mathematics positioned her perfectly to understand the logic, but it was her mindset that truly set her apart. She didn't see a glorified calculator. She saw a symbol manipulation device, and she saw the human programmers not as mere operators, but as communicators trying to solve complex problems. She envisioned a future where programming wasn't an exclusive priesthood of number crunchers who understood the machine's inner secrets, but a practical tool accessible to a wider range of problem solvers. This vision directly challenged the dominant culture, a culture that saw the machine as the master and the human as its servant. Hopper's frustration reached a boiling point in the early 1950s while working on the UNIVAC Y, one of the first commercial electronic computers. The problem was one of immense inefficiency. Every time she or her team started a new program, they found themselves writing the same pieces of code over and over again. The instructions to calculate a sign, to sort a list, to perform a common statistical test. Each time this subroutine had to be manually translated into the machine's specific, unforgiving numeric code. It was incredibly wasteful, time-consuming, and because it was done by hand, horribly prone to errors. An entire project could be derailed by a single misplaced digit. This was the critical juncture. Faced with this constant, frustrating repetition, Hopper had her revolutionary insight. She asked a simple but profound question. Why are we doing this over and over? The computer should be able to do it for us. Her specific action was to propose, and then build, the world's first compiler. In 1952, she developed what she called the ASIO system. It was a program whose job was to write other programs. A programmer could now write instructions using a more intuitive symbolic vocabulary, using English-like words for commands and familiar mathematical symbols. The A0 compiler would then take this source code, look up each command in a library of pre-written and pre-tested machine code subroutines, and automatically assemble the final, executable binary program. It was like having a flawless, lightning-fast translator and librarian working for you. The resistance she faced was immediate. Her superiors famously told her, Machines can't understand English words. They were stuck in the mindset that computers could only do arithmetic. But Hopper knew better. She understood that computers manipulate symbols, and whether those symbols were numbers or words was irrelevant. This was revolutionary for three key reasons. First, it introduced abstraction. The programmer no longer needed to know the intimate details of the computer's hardware, its specific wiring, or its unique instruction set. A thick layer was placed between the human and the machine, hiding the complexity and allowing the programmer to focus on the problem, not the tool. Second, it championed reusability. The A0's library of subroutines was the forerunner of all modern software libraries. Code, once written and debugged, could be stored and reused by anyone forever. This single idea completely changed the economics of software development. It shifted the industry from a world of bespoke, one-off artisanal projects to one of scalable industrial production. And third, it planted the seed of portability. If a program was written for her compiler, you could, in theory, make it run on a completely different computer simply by swapping out the compiler's library with one written for the new machine. The original program wouldn't have to change at all. This concept directly led to her later, crucial work in the development of COBOL, a business-oriented language designed from the ground up to be machine-independent, which would go on to run the world's financial and business systems for decades. So why isn't Grace Hopper a household name on par with Bill Gates or Steve Jobs? Her relative obscurity is a classic case of systemic bias, favoring certain kinds of stories and certain kinds of innovators. First, there was the hardware is king bias. In the early days, the heroes of computing were the engineers who built the machines. The focus was on transistors, vacuum tubes, and architecture. Software was seen as a secondary, almost clerical task, the instructions you fed into the important creation. Hopper's work on the how of programming was considered less glamorous, less tangible than the physical hardware itself. Second was the institutional absorption of credit. COBOL, the language that embodied her philosophy, wasn't created by her alone. It was designed by a committee, Codacil. While Hopper's ideas and her earlier language, Flowmatic, were the undeniable foundation, the credit for the final product became diffuse, attributed to a faceless consortium. Her individual foundational genius was absorbed by the bureaucracy, a common fate for innovators working within large organizations. A committee, by its very nature, obscures the sharp edges of individual contribution, smoothing them into a bland, collective achievement. Finally, there's the undeniable role of gender and the great man narrative of history. As a woman in the overwhelmingly male domains of the military and early computing, Hopper constantly defied expectations. While she was highly respected by those who worked with her, her public image was often softened, shaped into the quirky, approachable Grandma COBOL. Stories of her handing out pieces of wire to represent a nanosecond were charming and effective teaching tools, but they risked reducing her legacy. They painted her as a beloved pedagogue, overshadowing the reality that she was a hard-nosed, visionary systems architect and a foundational theorist of software itself. Today, thankfully, Grace Hopper's modern reckoning is well underway, especially within the tech community that owes her so much. The annual Grace Hopper celebration is the world's largest gathering of women in computing, a vibrant testament to her enduring influence. Her true legacy is woven into the very fabric of the modern software industry. The idea that programming languages should be human-centric, that code should be reusable, and that software should be portable across different platforms. These are not just best practices. They are the foundational pillars that Hopper helped erect. She represents the unsung army of problem solvers who focus on usability, accessibility, and communication. The people who turn raw technological power into tools the world can actually use. Her story forces us to look past the glowing screens and silicon chips to see the elegant layers of language and logic that truly make our digital world work. The history of technology is filled with figures like Grace Hopper, who focused not just on invention, but on making those inventions usable for everyone. Who else deserves to be pulled from the footnotes into the headlines? Share their story in the comments below. Thanks for watching. Subscribe to The Unsung for more stories from the bylines of history.